This is ACT Math. ACT Math Additional Concepts, Complex Numbers. Complex numbers show up not all that frequently on the ACT. Fortunately, when they do show up, if you know some pretty basic information about complex numbers, the complex numbers questions that do show up are actually rather simple and can usually be answered rather quickly as well. So in terms of what we're going to do here, obviously first we're going to go ahead and write down complex numbers. And the first thing that we should probably talk about is the standard form of a complex number. Standard form of a complex number, I'm going to write that down, standard form of a complex number. And standard form of a complex number is a plus bi. A plus bi, where a is the real part. We call b the imaginary part. And of course I is the imaginary unit. We will talk a little bit more about the imaginary unit in a moment, but most of you will know that the imaginary unit is the square root of -1. You can also sometimes see this defined as I squared equals -1. I squared equals -1. So again, it is important to note that the b itself is called the imaginary part. The b is sort of the coefficient in front of the I, telling us how many imaginary parts the complex number has. B is itself a real number, but again, it is the real number that describes the number of imaginary units we have in our complex number. So for instance, one of the things you may need to do is, if you are given a complex number, you might have to identify. So let's write this down, identifying A and B. So let's say here, we'll do a few examples here. So I'm going to draw a 3-column T-chart here. And we'll do this and this and this. So we'll start with a really simple one. Let's say we have 3 plus 2i. So you might need to be able to determine that your 3 is the real part and your positive 2 is the imaginary part. What about -4 minus I? Try that one out. See if you can identify A and B correctly. Of course, A here is -4 and B is going to be -1. Obviously, this complex number could be written as -4 plus -1 times I. So your A is obviously the 4 and the B is the -1. The -1 is in the B position. Now, if you get something like, let's say, just 8, well, it's important to understand that the number 8 still can be considered a complex number. It's just a complex number in which your imaginary part is 0, right? 8 could be written as, I'm going to do this sort of in this ghosted way here, 8 could be written as 8 plus 0i. There are no imaginary parts to that number. In the same way, if you had something like -4i, well, now your real part is 0 and your imaginary part is -4. Trickiest examples here are going to come maybe when you have fractions. So let's say you have something like 2 minus 6i all over 3. Well, if you clean this up a little bit using some typical fraction skills, we can split this. Actually, I'll do plus -6 over 3i. We can split this single fraction up into 2 separate fractions, and now we should be able to see that our A is 2/3 and our B is -2. So that's how we may identify A and B. Actually, the very trickiest of these questions will involve fractions in which you have a complex number in both the numerator and the denominator, and we will take a look at an example like that in a moment. Now, in terms of the imaginary unit, so I and the I and the pattern of 4 in the I powers. So let's start just by talking about I itself. So remember that I'm going to write that definition again. I is the square root of -1, or we could also say that I squared equals -1. So what does I allow us to do? It allows us to simplify the square root of negative numbers. So if I have something like the square root of -72, what I can do, there's multiple ways that I could break this down, but one of those ways is that I can first of all write the -72 as the product of -1 and 72. I can then break the two of those factors into their own square roots. That is a very common and very basic property of square roots, that the square root of a product can be written as the individual square roots of each factor in the product. So now, of course, I have an I here. And now breaking this root 72 down, there are calculator programs that can do this for you. But if you want to know how to break down the square root of a non-perfect square, the way to do it is either, so I'm going to write I times, either we can break 72 down into 36 and 2. Why am I using 36 and 2? Because 36 is a perfect square. So what I'm trying to do is I'm trying to find the largest perfect square that goes into 72. 36 fits that bill, and of course 36 is 6, so all of this becomes 6i root 2. So again, when you're looking at a number, for instance, like 48, if you know that 16 goes into 48, 16 is the largest perfect square that goes into 48, and 16 times 3 gives us 48, so I can break root 48 down in that way. Find the largest perfect square that goes into 48 that's a factor of 48. The other way that I can do this is with prime factorization. For instance, if I take 72 and I prime factorize it into, let's say, 2 and 36, and then maybe 18 and 2, and then maybe 9 and 2, and then maybe 3 and 3, and then step back and look at all of my prime factors, I have 3 2s and 2 3s. So what I'm going to do is I'm going to write 2 times 2 times 2 times 3 times 3. And remember, every time you see a pair under a square root, a pair of numbers being multiplied, two of the same numbers being multiplied, I can take those out, one of those, out of the square root. So I can take out a 2 for the 2 2s that show up here, and I can take out a 3 for the 2 3s that show up here, and of course I end up with 6 root 2. So that's just a little mini lesson, sort of side lesson about how we can break down square roots, not directly related to imaginary numbers and complex numbers, but we will need to know one or both of those processes. So let's have you do an example on your own. Let's try something like the square root of, let's do 84. So the square root of 84. So again, negative 84. Let's do a negative 84. Negative 84. So obviously we can first think of the square root of negative 84 as -1 times 84. That is the square root of -1 times the square root of 84. So of course we have an I here. Now in terms of 84, trying to find a perfect square that goes into 84, you know what? I can't tell right off the bat what perfect square goes into 84. So instead of doing the question that way with the perfect square method, I'm going to use the prime factorization method here. So I know that 2 and 42 go into 84, and then 7 and 6 go into 42, and then 3 and 2. So what I'm going to do is I'm going to do I times the square root of 2, 7, 3, 2. So 2 times 2 times 7 times 3. So remember, I can take one of those 2's out, and what I end up with is I end up with 2i root 21. I can't do anything with that 7 and that 3 inside the square root, so I just leave those 2 in there. So 2i root 21 is the square root of negative 84 simplified. Now in terms of the pattern of 4 in the powers of I, so let's first of all look at I to the first, I to the second, I to the third, I to the fourth. This is, or should be, fairly simple. Obviously, I to the 1 is just I. You could write it as root -1. I'm going to write it as I. I squared, we already know that I squared is -1 because I squared is the square root of -1 times the square root of -1, which is -1. I cubed, you can just think of I cubed as being I times I squared, right? If we multiply one I times two other i's, we will get I cubed. So I times I squared is I times I squared, which is -I, right? I times -1, I to the first times I squared will give us I cubed. So I times -1 is -I. And then, of course, I to the fourth, probably easiest way to think about that, I to the fourth is I squared times I squared. I squared is -1, so -1 times -1 is +1. Those are the first four powers of I. Now, here's what happens when we go to higher powers of I. I'm going to do I to the 5th, 6th, 7th, and 8th. The same thing keeps happening. Remember that I to the 5th can be thought of as I to the 1st times I to the 4th, right? I to the 1st times I to the 4th will equal I to the 5th. That's just simple exponent rules. We have the same base. We are just adding our exponents. Well, I times 1, I to the 1st times I to the 4th, I times 1 is just I again. I to the 6th, we could think of probably mostly easily as I to the 4th times I squared. That is 1 times -1, so we get -1. I to the 7th, we could think of as multiplying these two together, right? I to the 4th times I to the 3rd will give us I to the 7th. Well, that is 1 times -I. 1 times -I is -I. And then I to the 8th can be thought of as I to the 4th times I to the 4th. I to the 4th times I to the 4th will give us I to the 8th, so we're back at 1. And indeed, we're going to write one more column here very quickly. 9, 10, 11, 12, I. If we keep going with this, we will get I, we will get -1, we will get -I, and we will get 1. So what we end up seeing is that for the powers of I, we get this repeating pattern. I, -1, -I, and 1, where every time we get to an exponent that is a multiple of 4, we land on that I, right? 4 is multiple of 4, 8 is multiple of 4, 12 is multiple of 4. Now, what do we do for these other three positions? Do we use multiples of 1, 2, and 3? No, we don't. That's not the way we do this. And for those of you that have done section 3 of the ACT math manual where we talked about remainders and patterns, you will know that we've got to use remainders on questions like this. So what we do on these questions, the general formula for these questions is, so I'm going to write formula. The formula is you take the power that you need and you divide that power by 4, which is the number of items in the repeating unit. The remainder tells you where you land. And what I mean by that is if your remainder is 1, you are on the -I. If your remainder, I'm going to write R equals. If your remainder is 2, you are on sorry, this is not correct. Sorry about that. If your remainder is 1, you land on I. If your remainder is 2, you land on -1. If your remainder is 3, you land on -I. And if your remainder is 0, you land on 1. Let's take a look at an example or two of this. So let's say we have I to the, 623rd. Now keep in mind, some calculators actually can handle this calculation. If you type in I to the 623rd, for instance, to perhaps the TI Inspire, the TI Inspire might tell you what you get here. And on other calculators, there are programs that you can download that will solve powers of I for you. We're going to do this the quote-unquote manual way, where what we do is we take 623, which is the power, we divide 623 by 4, and we find our remainder. Now I'm going to do this in two different ways. So one of the ways that I'm going to do this is I'm going to use my TI-84's built-in remainders function. The built-in remainders function, I just need to go to Math, and then over to the number menu, and then down to where it says remainder. I could also have scrolled up there to get to the bottom of that list. So I'm on remainder, I hit enter. So what I'm going to do is 6, 2, 3, and then a comma, and then a 4. And I'm going to hit enter, and I get that my remainder is 3. So whatever the quotient is, I don't know what the quotient is. I know my remainder is 3, which means, remember, that means I'm going to land on that negative I. So I know that I to the 623 is equal to negative I according to that pattern. Now, in terms of doing this the other way, in case your calculator does not have a remainder function, although a lot of calculators do, what we're going to do is we're going to do 623 divided by 4. Some students will try to use the decimal there, and in this case, if you understand that that 0.75 means you have a remainder of 3, it's perfectly fine to stop there and be done with it. But I am going to show you that what we can also do is we can take the whole number result, 155, we can multiply that result by the denominator. And what that gives us, 155 times 4, is 620. And 620 is the highest multiple of 4 that is less than 623. So the 620, remember we said that every time we land on a multiple of 4, we're going to be at the 1 in our pattern, right? So the 620, I to the, I'm going to write this up here, I to the 620 would be the 1. Well, right after that, at 621, the pattern would start over again. So we have a 1, and then we go back to I, and then I to the 622, we have negative 1. That's the next item in our pattern. And then I to the 623, we would land on that negative I. So the pattern had ended there at that power that was a multiple of 4. And then we go 1, 2, 3. In other words, our remainder was 3, which we could have figured out simply by doing 623 minus 620. And we get a remainder of 3, which means, again, we're on the negative I. Let's have you do one of these on your own. Let's do I to the 344th plus I to the 320, let's say 22nd. So go ahead and do this. Remember, you got to use the remainders function in your calculator, or you can also use the sequence that I just did here. So I'm going to do this very quickly. The reason I can do this very quickly is because I know that 344 is a multiple of 4. And by the way, this is yet another way you could do these questions. Multiples of 4 always have the last 2 digits of the number are divisible by 4. And I know 44 is divisible by 4. So I know that 344 is divisible by 4, which means 344 is a multiple of 4, which means I'm going to be landing on that last item in the pattern where the remainder is 0. So my last item in the pattern is the 1. So I'm going to write down 1 for that first item. For this second power, again, I'm going to use my knowledge of multiples of 4. I know that 320 would be a multiple of 4 because the last 2 digits are a multiple of 4, which means that 322 is 2 above a multiple of 4, which means that when I divide 322 by 4, I'm going to get a remainder of 2. Well, when my remainder is 2, I'm at the second item in my pattern, which is negative 1, which means I am adding to my 1 a negative 1, which means the answer here is 0. So again, multiple ways that you can go about figuring out the powers of I. There are ways to use the calculator, there are ways to not use the calculator. You probably should be aware of all of those ways. We need to talk about complex number arithmetic. That's simply adding, subtracting, multiplying, and dividing complex numbers. So with addition and subtraction, I guess we'll start there. So with addition and subtraction, all you have to do is add / subtract, and I'm going to put this in quotes, like parts. In other words, you have to do real with real, and imaginary with imaginary. So as a very quick, simple example, hopefully it will be simple, let's do 3 minus 2i minus 5 plus 3i. So all I am going to do here is I'm going to, first of all, distribute that negative to these two terms to clean this up a little bit. So I get 3 minus 2i minus 5 minus 3i. And again, combining like parts, there's my two real parts. So 3 minus 5 is negative 2, and then negative 2i minus 3i is negative 5i. Now, for those of you who have TI-84s or similar calculators, you should know that your calculator does have a complex mode. So if you go to mode and you go to, I don't know, the 5th or 6th row down there, maybe the 7th row, you have a plus bi. Generally, your calculator, for the purposes of the ACT, should be in complex mode. To do complex arithmetic, you actually don't even need to be in complex mode, but I would suggest going down to that row, putting your cursor over a plus bi, and hitting enter to get your calculator in complex mode. What we can do is we can actually enter this calculation into our calculator exactly as it appears on the page. I do parentheses, 3 minus 2. Now your I is right here. It's a little blue I above the decimal key. So we're going to hit second and then that decimal point. So 3 minus 2i, and then we are subtracting from that 5. And notice I am using parentheses. I don't want to make any careless mistakes here. Plus 3, and again, second function, and the decimal point. I am going to close the parentheses. It's a best practice. So I get negative 2 minus 5i. So the calculator did the calculation for me. So that's adding and subtracting. Just add or subtract the like parts. In terms of multiplying, usually you are going to have to use a FOIL-like process. So I'll use actually the same two complex numbers, 3 minus 2i times 5 plus 3i. So what we generally have to do if we have a question that is structured like this is we multiply our first terms, and of course we get 15. We multiply our outer terms, and of course we get 9i. We multiply our inner terms, and of course we get negative 10i. And then we get, for our last terms, that's going to be negative 6i squared. Now, cleaning up a little bit, we can combine these like parts. 9i minus 10i is negative I. We still have that 15 out there. And then, of course, what we need to do here is we need to be very careful. That I squared, remember, I squared is negative 1. So this is going to be 15 minus I minus 6, but then we're multiplying by that negative 1. So this all becomes 15 minus I plus 6, which equals 21 minus I. Again, I can check this in the calculator. I could punch this all into the calculator, but since the TI-84 has this beautiful copy-paste option, I just arrowed up and hit enter once the line here was highlighted. And now what I'm going to do is I'm going to go into the pasted line, and I'm just going to go over the minus, hit delete, and then hit enter, and of course I get 21 minus I, so I have confirmed that what I did was correct. Whether you use the calculator or you do this stuff manually, it doesn't matter, but you should know that your calculator can do a lot of these calculations for you in case you need to check or in case you're getting tired and you're worried about making a careless mistake. Now, in terms of division or dividing, so I had mentioned before that some of the toughest cases come up when you have something like, 3 plus I over 5 minus 2I. We'll look at this example in a moment, but before we get to how we would clean all of this up, how we would actually do this division, we need to talk about conjugates, complex conjugates. And you just need to understand that when we have a complex number like a plus bi, its conjugate is simply a minus bi, and if we had a minus bi, its conjugate would simply be a plus bi. In other words, the definition of a complex conjugate is simply the same complex number except with a different sign on the imaginary part. So if I have 5 minus 2i, its conjugate would be 5 plus 2i, and indeed we use complex conjugates to divide complex numbers as follows. So we've got 3 plus I, over 5 minus 2i. What I'm going to do, and you'll see in a moment why I'm doing this, I'm going to multiply both numerator and denominator by 5 plus 2i, which is, again, the conjugate of the denominator. Keep in mind that 5 plus 2i over 5 plus 2i simply equals 1, which means that I'm not changing the value of my original fraction. If I'm multiplying by 1 doesn't do anything to the value of the original fraction. I'm just going to change the form of that original fraction. Now watch what happens. Up there in the numerator, I'm going to get 15. I'm just foiling this out. So there's 15 plus 6i plus 5i, and then I times 2i, so that is plus 2i squared. I'll clean that all up in a second. Do keep in mind I could have done all that in the calculator. I'm just doing this manually so that you can see what the process looks like, but perfectly fine to use the calculator. Now here, watch what happens. So I get 5 times 5, which is 25. I get 5 times positive 2i, which is positive 10i. And then in the middle here, I get negative 10i. And then the last terms, negative 2i, positive 2i, that is going to be negative 4i squared. Well, first thing to notice, and probably most important thing to notice, is that my two middle terms here cancel each other out. In other words, I have eliminated my I apart. Now you might be looking at this I squared and saying, well, you didn't eliminate your I apart, but I did, because remember that I squared is simply negative 1. And that really is one of the most significant things about how conjugates relate to each other. When we multiply complex conjugates by each other, we eliminate the imaginary part of the complex number and we are left with only a real part. So if I start cleaning all this up, I get 15 plus 11i plus 2i squared, which is actually just minus 2, right? Because I squared is negative 1, 2 times negative 1 is negative 2. And then in the denominator, I get 25 minus 4 times negative 1. So cleaning up a little bit more, 15 minus 2 is 13 plus 11i over, this is going to be 25 plus 4. 4 times negative 1 is negative 4 minus negative 4. So 25 plus 4, that's 29. And now watch what I can do. We did something similar to what we're about to do in an earlier example. We're just going to split the complex number into its pure standard form. So I can now see my A is 13 over 29 and my B is 11 over 29. So that was the point of this entire process, was to get the I out of the denominator. In other words, we're sort of rationalizing the denominator and get our complex number into standard form. That is what multiplying numerator and denominator by the complex conjugate will do for us. So that is how we divide complex numbers. Do keep in mind that the calculator could have done all of this. In fact, I'm going to do this as follows. 3 plus I, that's second function I. Notice that I am putting that in parentheses, divided by parentheses. Very important to use parentheses here. 5 minus 2 and I. And when I hit enter, I do get this very ugly fraction, 0.44 plus 0.37i. But if I hit math, enter, enter, I convert the decimal form to the fractional form, and I can see exactly what I got over here. So the calculator once again has confirmed that I did this all correctly. Now, in terms of graphing numbers on the complex plane, I am going to go to a new page here, and I'm going to write down graphing complex numbers. Normally when we graph numbers on the xy coordinate plane, the x and the y axis both represent real numbers. X is a real number and y is a real number. However, when we graph on the complex plane is not the same as this regular old xy coordinate plane. In the complex plane, what we have is we have a horizontal axis where we plot A, which is our real part, and we have a vertical axis, which is B, where we graph our imaginary part. So I'm going to do some tick marks here, hopefully making this fairly nice and neat. I don't need too many on the x-axis there. That looks pretty good. So what all of these tick marks on the x-axis represent is just the real number 1 and then 2 and then 3 and blah, blah, blah. On the y-axis, here we have 1i, here we have 2i, here we have 3i, and then of course negative 1i, negative 2i. So what we're really graphing on the vertical axis here, again, is that b in front of the I, the imaginary part. So for instance, if I were to lay down this number right here, this point right here, well, I can see that the real part there is going to be 1, 2, 3, 4, 5, 6. The imaginary part there is going to be 3. So that point represents the complex number 6 plus 3i. Some students will say, why can't I write it as 6, 3i? And the answer is, you can if you want. That's just not the convention. We write complex numbers in standard form, a plus bi. If it helps you to think of this point as 6, 3i, then by all means go ahead and think of the point like that. But the conventional way to write that point would be 6 plus 3i. I'm going to plot another point here, and then you should try on your own to figure out what this point is. So that point right there. Go ahead and pause the video and tell me what that point would be. And of course that point would be negative 3 minus 4i, right? We are at 1, 2, negative 3 on the real axis. We are at 1, 2, 3, negative 4 on the imaginary axis. So that point is 3 minus 4i. That is how we graph complex numbers. One slightly more advanced concept that has shown up when it comes to graphing complex numbers has been distance between complex numbers. There are multiple ways to do questions like this. In fact, some of you may have calculator programs that can help you with this particular process. However, the way that I recommend doing this, the way that I want my students to know how to do this is we're just going to use right triangles. So what I'm going to do is I'm going to draw a horizontal segment that connects the negative 3 minus 4i and the vertical segment that connects negative 3 minus 4i and 6 plus 3i. I'm going to draw a horizontal segment that connects them and a vertical segment that connects them. And then, of course, when I complete that triangle, the hypotenuse of the triangle is going to be the distance between those 2 points. So to find distance between complex numbers, all we do is draw a right triangle to connect points and use Pythagorean theorem. So how many units is it from negative 3 to 6? That is 9 units. How many units is it from negative 4? We're just using the imaginary part here. So negative 4 up to 3, that is 7 units. So all I do, Pythagorean-wise, would be that the distance between these 2 points, I'm going to call that distance squared, equals 9 squared plus 7 squared. That is simply the Pythagorean theorem. And now I am sort of off to the races here. D squared equals 81 plus 49. 81 plus 49, I am going to do that in the calculator. 81 plus 49, and I get 130. 130, so D squared equals 130, and that means that D equals the square root of 130. Does the square root of 130 break down? 10 and 13, 5 and 2. No, it does not break down. So we would just leave square root of 130 as is. So this distance is the square root of 130. The only other thing, and this would be the most advanced thing that ACT could test, and that is the absolute value, otherwise known as the modulus of a complex number. So we are talking absolute value of something like a plus bi. one thing that most students do understand about regular old absolute values, like for instance, the absolute value of -3, students do understand that that equals 3. And one of the things that almost all students have been taught at some point along the way is that we can also think of an absolute value as the distance from 0 on the number line. So -3 there, 3 there. So this distance here is 3. This distance here is 3. And that is why both the absolute value of +3 equals 3 and the absolute value of -3 equals 3, because both -3 and 3 are a distance of 3 units from 0 on the number line. Really no different when it comes to complex numbers graphed on the complex plane, except we are using the origin as our sort of reference point. So what do I mean by that? Let's just do something fairly simple here. Let's do this point here, which is 3 plus 2i, right? 3 on the real, 2 on the imaginary. Real, imaginary. So 3 plus 2i, let's say we were being asked for the absolute value of 3 plus 2i. Well, instead of the real number line where we find distance from 0, what we are doing is we're finding the distance of 3 plus 2i, our complex number. We're finding the distance from that number to the origin. The origin is 0 plus 0i. So all we have to do is what we did on the previous question. Connect the 2 points in a right triangle with a horizontal segment and a vertical segment. Then we get this distance here, and indeed that distance will be the absolute value. So what are we going to do here? Let's do what we did before. D squared equals, this horizontal distance here is going to be 3 units. The vertical distance is going to be 2 units. So I'm going to do that d squared equals 3 squared plus 2 squared. And d squared equals 9 plus 4. D squared equals 13. Root, and I get that d equals 13. So the absolute value of 3 plus 2i, which is simply defined as the distance between 3 plus 2i and the origin, would be, forgot my root there, would be root 13. There is a chance that you will see the more generic, let's say, formula for the modulus of a complex number. So let me do this in this way. I'm going to sort of draw the kind of the same thing that we had up here. So let's say 1, 2, actually, it doesn't even matter. Let's not even draw tick marks. I apologize. Let's just draw a random point there, and let's call that point A plus BI. Well, remember, the horizontal segment that you draw is going to be A, right? Because A is your real part, and whatever the real part is the distance along the horizontal axis, or, you know, the x-axis that you have to go to get to that point. And then, of course, the B is the distance from that horizontal axis up or down to the complex point that you are talking about, to the complex number you're talking about. And then, of course, you have your hypotenuse, which would be the distance. So what we should be able to see is that the absolute value of a plus bi, which again is simply the distance from the origin, I'll just say that's d squared, so let's call this d for distance, is going to be a squared plus b squared. And in order to solve for d itself, we just square root both sides, and we get that d equals the square root of a squared plus b squared, and there is the formula. We know that if we want to find the absolute value of any complex number, we can just find the square root of this number squared plus this number squared. So do you need to memorize this formula? No, generally you don't. In fact, the question that I am thinking of on which this formula was involved, the formula was actually given. The reason that I'm walking you through this process is because sometimes when the formula is given, students get confused and students forget that they know this process up here, which, you know, if you're given the numbers, if you're given the 3 and the 2 because you know the complex number, then just do what you know how to do with the Pythagorean theorem and forget about the formula itself. Having said that, if you know the formula and you understand the formula, it might be easier to do some of these questions using the formula. Maybe not necessarily easier, but possibly more efficient. That is it for complex numbers. So again, we do need to know what a complex number is, what its standard form is. We do need to know how to identify A and B. We need to know I and the powers of I. We need to know how to do some complex number arithmetic, and then we need to know just a little bit about how we graph complex numbers on the imaginary plane. Most of this stuff hopefully did not seem too complex. As I said at the very beginning, complex number questions do not tend to be all that hard if you know this information. They also do not show up very commonly, but if you are going for a phenomenally high score, you do need to know and understand this information.